Yeah, thanks very much, Marcus. Thanks for hosting this webinar. It's my distinct pleasure to talk today about complexes exhibiting sigma holes, and we will look at them in SeeSAR, and hopefully we'll be able to give you a little bit of an alternative description on them. Sigma holes have been hyped quite a bit in the past in the literature, and they have been attributed for, in some complexes anyway, a greater increase in affinity, and hopefully we will, as I said, give you an alternative description on why that may happen, and look at these very interesting interactions in a little more detail and maybe shed a little different light on them. We had the poll, so let's dig right in. I would like to give you initially a quick overview of what we are dealing with here. So the sigma hole gives rise to an interaction which is known as the halogen bond, and these have obviously been around for a very long time and have been known for decades, but they have increasingly been mentioned in the literature only since the beginning of the 1990s. The first mention of a halogen bond was in the 1950s in equimolar bromine dioxane crystals, where the oxygen-bromine distance was below the sum of the van der Waals radii. So the authors of that publication reasoned that this must be some sort of very special type of interaction. In 2007, then, there was a seminal paper by Tim Clark of the University of Erlangen, which was the first comprehensive review on halogen bonds and the sigma hole effect. And this sparked an exponential increase in publications that dealt with the keyword halogen bond or halogen bond and computation. Obviously, halogens do play important roles in biological systems and also, of course, in drug molecules. In FDA-approved drugs between 1988 and 2006, 57 of these drug molecules contain fluorine, 38% chlorine, and 4% and 1% bromine and iodine, respectively. Now, chlorine is potentially the more reactive of all the other halides, and the reason why we have only such few bromine and iodine atoms in these molecules is because they do add a lot of weight, and we get into molecular obesity very quickly if we want to add lipophilicity simply through the weight of the atom. But they do have very important properties, and that's why they initially have been introduced in drug molecules. Namely, they fill very nicely hydrophobic pockets. Of course, the presence of a halogen atom does improve oral absorption and helping crossing the blood-brain barrier, and they also prolong drug lifetime. But just recently, publications have been indicating that halogen atoms are introduced to deliberately form these so-called halogen bonds, and one is hoping that this type of interaction would increase affinity. So we can say that a halogen bond is an interaction between a halogen, usually chlorine, bromine, or iodine, attached to a carbon, is interacting with a Lewis base that is also attached to a carbon, typically with a distance of about 3 angstrom. And as we will see later, there can be quite some fluctuation around this distance. So the question remains, why do seemingly negatively charged atoms, such as these halogens, interact with Lewis bases? And the reason for this is the anisotropy of the electron density of the halogen atom. We found this nice description here of a halogen bond in this publication, where a halogen bond occurs where there is evidence of a net attractive interaction between an electrophilic region associated with a halogen atom in a molecular entity and a nucleophilic region in another or the same molecular entity. This means that they make negatively charged atoms, such as halogens, act as if they were positively charged. And the explanation for this is the orbital configuration here of the halide atom. We have the px orbital here, we have the py orbital here. They are both filled with 2 electrons respectively, but the pz orbital, which is in the plane of the carbon halide bond, is only singularly filled with 1 electron, which is usually in near the sigma orbital of the carbon. It is interacting with the sigma orbital of the carbon. So therefore, we have 1 lobe of the pz orbital, which is not filled with an electron, and therefore bears some positive charge, and this is the sigma hole. So maybe this picture shows it a little more clearly. We have the halogen atom here, the carbon bonds to the halogen, and the sigma hole is right here in the elongation of the bond of the carbon halogen, which then can attract a Lewis base. This is again positive. The electrostatic potential is red. And here the negative electrostatic potential is shown in blue, which is along the waist of the halogen atom, or the center equator here. And this attracts or can attract a Lewis acid. Now, why did I put the fluorine in brackets? Fluorine typically does not form a sigma hole. We have here again the situation for bromine with the 2 px and y orbitals, the pz orbital in the plane of this bond, the carbon halogen bond, and the 4s orbital. But in the fluorine atom, we have more sp hybridized, or the bonding orbital has more sp character, which leaves a lot of 2s electron density, which then again depletes the sigma hole. And also the fluorine atom is a little too small to be polarized. Bromine and iodine atoms are larger and more easily polarizable, which is also shown here in calculations of methane, chloromethane, bromomethane, and iodomethane. Pay attention here, the color is inverted, so positive electrostatic potential is shown in blue. And as you can see, this is only the case for the bromomethane and even more pronounced for the iodomethane. There is no sigma hole here in chloromethane. However, if you would substitute the hydrogens for fluorine, which are obviously very electronegative, they would draw this electron density away, and the sigma hole would become more pronounced. In 2010, researchers did a statistical study on the types of interactions of halogens with protein, or in the protein environment. And they took the PDB 2009 database and selected X-ray and NMR structures of resolution 3 angstrom or better. And in this subset, they found that more than 2,000 ligands were halogenated. Of those, they selected those with a halogen bond distance smaller than the sum of the van der Waals radii, and the halogen bond angle was larger than 140 degrees. So unfortunately, that left them only with roughly 10% of the crystal structures. 240 crystal structures of proteins were extracted, and this led to the following distribution here. 53% of halogen atoms interacted to some degree with an oxygen, of which roughly 3/4 were with the backbone of the protein, and only some with serine and threonine, where there's a lot of competition with solvent molecules. 33% were with between the halogen and a pi system, such as in tyrosine or phenylalanine or an amide, and only 5% and 9% respectively were with sulfur, such as in methionine, or nitrogen, such as in histidine. So because this is a very small number, one might argue that this might drown in the noise, but at least it gives a little bit of a better picture of the distribution for this type of interaction. Let's talk a little bit about the geometries here. A lot of computations have been dealing with these types of interactions, halogen bonds, and a typical model system for a protein backbone is N-methylacetamide, and this interaction here was done between chlorobenzene, bromobenzene, and iodobenzene. These are shown in green, red, and purple, respectively. By the way, this is a cartoon from the paper here that I drew. But it shows that the larger the halogen atom gets, the more pronounced the complex formation energy is. However, this was done in vacuum, as the headline here says. So once you put this in water, due to the quenching effect, the complex formation energy will diminish significantly. And we would argue as well that due to solvent effects, if you picture this is a backbone, oxygen is dehydrated, the halogen atom is also dehydrated when you take it out of the solvent. This bond formation energy will hardly overcompensate the dehydration cost for both these atoms. There is also a strong angular dependence on the complex formation energy. Again, these were calculations done in vacuum, so very likely this might be very different in the solvent. There's not very many things known about how halogen bonds actually do behave in the solvent. But the minimum angle here, or minimum energy angle, is around 180 degrees, and as soon as you move away from this, you lose a lot of energy. So I believe we have a second poll now.
That's right. So our second poll at this point would ask you, if you had a genie in a bottle, what would it do for you? What would she do for you? If I could do magic, I would minimize small molecules and the protein, do flexible docking, model interactions such as this halogen bonding scenario here, or some other atypical scenarios such as CHO bonds, etc. Do on-the-fly pattern checking maybe, or something else. Would be great if you could quickly give us a hint here. Okay, almost half of the people have clicked. I'm going to close this in 3, 2, 1, 0 seconds and convey the results. So we have more or less at the same level the flexible docking problem, and a ubiquitous problem that always needs good approaches to be tackled with. But the winner here, slight winner, is to exactly model such unusual interactions here. Thanks very much for this input, and I will dim this out and hand back over to Carsten.
Yes, thank you very much. So interesting that this is still obviously a very important question. Hopefully we will be able to give you an answer to this and show you that it might not be so important to really explicitly model these types of interactions, because in protein ligand complexes, most of the driving force for binding does come from dehydration effects. Okay, so here we have a list of complexes that we looked at in this study. This is by far a comprehensive list, but it is some complexes that we looked at, and we looked at them in SeeSAR. These are only complexes of which we could find either a potency, a dissociation constant, or an inhibition constant. As you hopefully can see, it's a little small, but the table is rather long. There is various types of interactions between the halogen atoms and the backbone or the protein. Most are with the backbone. Some are with aromatic amino acids such as phenylalanine or tyrosine, and some are explicitly with single individual amino acids such as methionine, glutamine, or histidine. Interestingly, as opposed to the slide I was showing earlier, we have a lot of iodine atoms here in these molecules, very likely because they don't only add a lot of lipophilicity to the compound, but they also form the strongest halogen bonds, at least in vacuum. So that might be the fact why they have been introduced, and there's also a great deal of bromine atoms here. If you remember the distance dependency on the complex formation, there is quite a variance here in this or distribution of distances for these complexes. Only very few exhibit the optimal distance between the halogen and the Lewis base. We do find a great deal of distances that are significantly larger than this optimal distance, even one that is, or several that are over 4 angstroms. Although you find in papers that it can be as large as 5 angstrom, but the calculation that we have seen shows clearly different. So we looked at these complexes in SeeSAR, and here we classified whether the estimated affinity in SeeSAR was in the right ballpark. I do realize that we set this the potency here quite in analogy with the affinity, and so therefore we assumed that we had a non-competitive inhibition situation of the enzymes, and therefore we can say roughly Ki is about the same numerical value as the IC50. For those complexes where we did not find a good correlation between the estimated affinity and the experimental one, we looked at the electron density, and for most of these complexes we found that the electron density was not great. So one might argue, for once, is this number real? And we also might argue that these distances might be completely different if we factor in that the electron density is not of good quality. Anyway, let's look at the first example here, isoflurane. As you might remember from the introduction, fluorine typically doesn't form a halogen bond. In this case, we have isoflurane, which is an anesthetic, and there are a lot of electron drawing groups on this molecule. But let's look at this in SeeSAR. We have SeeSAR here, and what you can see is the molecule in the pocket. To the left-hand side, we have a table where you see the molecule name, and you also see the estimated affinity. Isoflurane binds experimentally with about 800 micromolar, so we are right in the correct ballpark here. And here are the 2 fluorine atoms that are opposite of the tyrosine phenyl ring. So one might argue, yeah, this could be a halogen bond, but even the authors of the publication in which I found this molecule, this complex, were questioning that indeed there is a halogen bond. We can check the distance here between the fluorine and the phenyl atoms, and this is between 3.3 and 3.4, 3.5 angstrom, so rather large. And especially if we look at the contribution for binding, we find that there is a minus 1.5 kilojoule per mole contribution from the desolvation of this hydrophobic fluorine atom, and a minus 3.4 for the atoms that are interacting with the fluorine, which we can see here. These are not even all of them, only 4 of the aromatic carbon atoms of the aromatic ring are interacting with the fluorine, but there are 2 more of the protein active site that are also dehydrated and that are quite happy that there is a hydrophobic entity next to them. This becomes even more apparent if we look at the binding surface here, colored in lipophilicity. Yellow means that there is no hydrophilic entity around, and we can see that there's only yellow, so there's no absolutely no contribution from any hydrophilic entity around. So this is clearly the hydrophobic effect that we are dealing with here, and it's not very likely that we do have any sort of halogen bonding here, which, as I mentioned, was also in the paper. So the second complex that we will look at is a Halogenpire complex with a chlorine involved. This is an active site thrombin inhibitor binding with 1 millimolar, and again here we are in the right ballpark. This scaffold here is the crystal structure, so you see that due to the optimization, the position of the chlorine atom has not changed much. And again, we can look at the distance here between the crystal structure and the phenyl ring, which is 3.73, and even a little bit more, 4.65. So again, we would argue that there is hardly any halogen bonding contributing here. There might be a very weak halogen bond, but it's unlikely that it contributes a lot to the affinity. Because if we look at the chlorine here, the chlorine bears a lot of a green affinity corona, which means that this atom contributes quite a lot to the affinity, and it does that through the desolvation, the dehydration, I should rather say, minus 2.8 from the chlorine and minus 3.0 for the receptor. So again, if we look at the interacting atoms here, let me quickly show this again. We see that only these two atoms are involved in this interaction between the chlorine and the protein. And if we look again at the binding site surface, we see that, let's turn this very slowly, we see that there is no blue again in this region. This is a very hydrophobic pocket in which the chlorine is very, very happy. So again here, this is clearly due to dehydration effects. The next example I would like to show is a tetrabromopire derived inhibitor for protein kinase CK2. To me, this looks a little bit like the Millennium Falcon. And here we have a little bit of difference between the crystal structure, which we see here, and the optimized ligand. So that might account for, again, some uncertainty in filling the electron density. If we look at the crystal structure, that's indeed the case as well. And let's look at the geometries of these bromine and backbone oxygen atoms. In this case, we have an almost perpendicular arrangement, so there's clearly no halogen bond present here. When we remind ourselves of the slide that I showed, the angular dependence and also the distance dependent, 4.35 is clearly too long. 3.39 is also a little bit too long, although in this case, well, actually, if we look at it, the sigma hole would be here, which is pointing away from this lobe of the electron lone pair of the oxygen. So I would argue that there is hardly any halogen bonding present here. This might actually be some sort of halogen bonding for this atom. A little bit shorter distance, the angle seems to be valid. So in this case, we actually might have some sort of halogen bonding present. If we look at this one, this contributes the most through the dehydration. And oops, sorry. If we look at the contribution here, we find again that only one aromatic carbon atom contributes to the dehydration. So it's questionable if this is indeed a Halogenpire complex, but other protein atoms contribute also more to the dehydration. So On average, these bromine atoms contribute about 6 kilojoules per mole through dehydration to the affinity here. So I would argue clearly that this is a much stronger pronounced effect than any halogen bond. If we look again at the surface, let's color this according to lipophilicity. We see that in the plane of this Millennium Falcon, there's very little blue, just a little bit below this bromine atom. But again, the sigma hole points towards this area here, clearly into the yellow arena, not so much into the blue. For this one here, this could be again a very weak halogen bond here, because there's some blue area here. But this helps quite a bit by in analyzing these complexes when you add the distances, and especially when you look at the surface colored by lipophilicity. Okay, then we have a complex with a backbone, iodine, oxygen. This is a inhibitor that are highly selective for the S1 site of serine 119 trypsin-like serine protease, and the PDB code is 1GJD. And here we have an interesting situation. We have a chlorine and we have an iodine, but the chlorine doesn't point anywhere near anything that could be an interaction in the form of a halogen bond. Everything is too far away, or the angle is not good enough. So you can see here there's some sort of backbone O, but it's way out of sight for the sigma hole. The bromine could potentially interact with the methionine S lone pair here, but actually it's penalized because it blocks this backbone oxygen, and which is expecting a hydrogen bond. So therefore there's penalty on this bromine, and also there's a water present. So the water has not been expelled from the active site, and this might also potentially weaken any halogen bond here. Let's look at the contributions. So we label this again. Actually, let's measure this first. So in the crystal structure, we have a distance of 3.67, which is quite long. The optimized structure is even a little bit longer. So it might be, again, due to the fact that the electron density has not been filled good enough, or sort of filled differently than it should be. And if we look at the contributions here, we see that on the receptor side we have a penalty this time. The penalty comes from this oxygen and also from the histidine here, which also expects a hydrogen bond. And one could argue that if indeed there was contribution from the halogen bond sort of formation, there is, if you remember the slide I showed in the beginning, there is negative electrostatic potential around the waist of the bromine atom, which would clearly not interfere very favorably with this histidine nitrogen lone pair. So here, this oxygen would expect a hydrogen bond, and therefore it maps its unhappiness onto this bromine atom. So lastly, I would like to show a MAP ERK kinase inhibitor, which does form interesting conformations here, or arrangements, sorry, with the backbone of the protein. In this ligand, we have two fluorine atoms on one ring, another fluorine atom on the second ring, and an iodine. And the iodine actually is supposed to form, that's what I found in the publication, a very strong halogen bond with the backbone of the receptor. But when I look at this from the geometry, so the distance seems to be okay. So we have a distance here between the iodine and the receptor oxygen of 3.1 angstrom. But if we look at the plane here, where the iodine is coming from, this is the plane of the lone pair of the oxygen. The iodine comes from below. So I would argue this is potentially not a very strong halogen bond, and is hardly contributing a lot to affinity. This complex does bind with 50 nanomolar. So in this case, we have an underestimation by SeeSAR. But if we look at the electron density, which we'll look in a second, we see that there's a great deal of uncertainty involved. So here, this is the binding situation. We can again look at the surface here. Let's look at the surface real quick. So again, here we do see a little blue spot, but the sigma hole is actually pointing right into the area of hydrophobicity. So again, also because of the fact that we have a large affinity corona that's coming from desolvation, this is very likely the driving force here. So let's look at the electron density of this complex. You can see that there is a great deal of uncertainty. There's areas where the ligand has been placed where there's no electron density, and areas which have been observed but which have not been filled in the calculation and so forth. So I would argue that this might be the case why SeeSAR is underestimating the affinity, because the hydrogen bonds are not exhibiting the correct geometries that it needs to overcompensate the desolvation cost. So now you're in for a treat. I'm giving you a snapshot of, or a sneak preview of SeeSAR 7.0. SeeSAR 7.0 will feature a lot of new interesting things, such as you can add rings in total to your ligand without having to build them up. This is not in this particular version yet, but it'll be in the final version. And we also have a multiple common substructure docking, which is a lot faster than the FlexX docking we have in there. And also it uses the information from the ligand in the pocket, so that the docked structures are a lot more reliable. You can see that there are 4 proteins loaded in SeeSAR. This is possible from version 6 on. And as you see in the movie in a second here, this is the protein alignment. So you'll be able to align these structures provided they have a sequence identity of more than 80%. And the ligands are below here, and I'll comment as the movie goes along. So the first thing is I select a ligand to be the center of the pocket. This pocket information is needed to calculate the estimated affinity. Then I go back to the proteins tab and align the proteins. And then I copy all the molecules of these proteins over to the molecules tab in order to do something with them, like edit and calculate the estimated affinity of all these. Then I remove the ones that are not in the right chain. So the B chain ligands I remove. And you can see there are 3 different ligands now, and I added the smallest one to build up and to the largest one, and later on then compare what I've built with the crystal structure. So you see that this is also a ligand that has 2 iodine atoms. One is forming potentially a halogen bond with the backbone. The other one is used to build up the ligand. Here I add a ring to this nitrogen atom. That goes very quick. I add another nitrogen and these two carbon handles. As you can see, the structure is growing into the surface, which I can correct. I don't have to, the docking will take care of that, but it shows very nicely how you can use the information of the torsional quality, which shows how well a torsion is distributed in the CSD. So here I did the multiple common substructure. I placed this ligand 10 times into the pocket. I save my session, and now I can calculate the estimated affinity for all of them, which is very quick. I sped this up a little bit for the video so you don't have to wait as long, but it's usually about the same. And here you see that the best placed structure is used to build up the second part of the molecule. So here I now use the surface also to guide my build, and I make the iodine into a carbon. I add another carbon, and I can do this simply by typing C on a keyboard when I have selected a bond or carbon. The triple bond I do by typing 3 on my keyboard. So it's a very simple and quick process. And here I have the oxygen handle, and I build up the phenyl ring now by selecting 2 carbons at the same time, typing C, and then this is a very quick process. I form the bond, and I select alternating bonds, type 2 on the keyboard, and there's my benzene ring. So in this case, I don't pay attention to the quality of the torsion so much. I simply show how you can place parts of the ligand by simply rotating around specific bonds to sort of give a starting point for the optimization. So the optimization is such that we optimize to the next local minimum, and sometimes this local minimum might be a little bit further away. So that's why I give it an initial starting point. I do a multiple common substructure docking again. This time only 2 placements were found. But as you can see, these are actually of good affinity. At least one of them is, if I remember correctly. So I'll move down to the bottom of the table. There we are. And you can see that placement 6_1 actually has good affinity. I can sort by the affinity to kind of flush it to the top. You have to click one more time. There it is. And you can see that this is indeed a very good placement. If we make the crystal structure a reference now, then we can see that the pose is very, very good, with the exception of the ring torsion, which is a little bit off, but the rest of the structure looks pretty much like the crystal structure. So this little video should have shown you how easy it is to use SeeSAR to guide your ideas and to build up a molecule, and especially how to use the estimated affinity to pick the right starting structure, and to look at the affinity coronas to identify potential points of improvement on the ligand side. Okay, this was the sneak preview of SeeSAR 7.0, which will be out very soon, so stay tuned with our website, and it'll be announced in all the channels, Facebook and LinkedIn and so forth, once SeeSAR 7.0 is out. Okay, this brings us already to the summary. So I hope we could show you, and obviously halogen bonds interactions are observed experimentally and calculated. There's been a lot of papers out in the literature which deal with this very interesting interaction. But based on the observations that we have made in SeeSAR, we believe that the amount of contributions to affinity by halogen bonds may be questioned, because the affinity is not the sum of the interactions. Rather, we see that the affinities likely stem from dehydration effects, as hopefully I could show you by looking at the affinity coronas of the halogen atoms involved, and also the lipophilic surface. So while SeeSAR doesn't explicitly calculate these halogen bonds because it only looks at hydrogen bonds and desolvation, the majority of the complexes in this study is okay with respect to the calculated versus experimental affinity. There's also an interesting blog post by Derek Lowe in the pipeline that deals with this topic, so you are welcome to check this out. And before I want to say a few closing remarks, I believe we have a last poll here, Marcus.
That's indeed the case. So, of course, we'd be interested in whether you guys have a little bit of a sharper eye now to these interactions. So let me just fire this up. Would you see the contribution of halogen bonding to affinity in a different light now, or not? Perhaps you were already very familiar with the energetic balances between the electronic effects that are computed in vacuum versus the affinity in water that's been measured. And yeah, we have 65% who have clicked. Don't be shy, give us a click. And I'm going to close in 3, 2, 1, 0 seconds. Very interesting. So yes, I think we could raise awareness for the bonding situation. 11% who did not change opinion or who have already been in sync with what has been talked about. But 50% at least were stimulated to read a little bit and drill into the literature a little bit more, which is a great result. I think we can be very happy with this outcome of this webinar. So I'm doing these out and hand over back to Carsten. Thanks very much, everyone, for clicking.
Yeah, there is an especially worthwhile reading paper by Michal Kolar and Pavel Obsha in Chemical Reviews 2016. They were not sure if not the desolvation changes took away a great deal of the favorable energies of the halogen bond. This is actually a very, very nice paper that is scientifically sound and that is worthwhile reading. I just wanted to mention that. And so we invite you to try this out yourself in SeeSAR and form your own opinion and maybe actually start a discussion about this. Every participant of the webinar will receive a 1-month license of SeeSAR for free, so you can go and look at these complexes yourself and try them out and form your maybe new opinion about this, maybe not. But anyway, you can go and see SAR yourself. And with that, I would like to close this webinar. And I guess we will have a few questions that Marcus and I will be answering. And hopefully this was valuable for you guys and you learned something, maybe something new today. Thanks very much, everyone, for listening.